Section 14.2, Using ConfigMaps and Secrets in Kubernetes. The 15-factor methodology recommends keeping code, configuration, and credentials always separate. Kubernetes fully embraces that principle and defines two APIs to handle configuration and credentials independently: ConfigMaps and Secrets. This section will introduce this new configuration strategy, which is provided natively by Kubernetes. Spring Boot provides native and flexible support for both ConfigMaps and Secrets. I'll show you how to work with ConfigMaps and their relationships with environment variables, which are still a valid configuration option in Kubernetes. You'll see that secrets are not really secret, and you'll learn what to do to make them really so. Finally, I'll go through a few options for dealing with configuration changes and propagating them to applications. Before moving on further, let's set the scene and start a local Kubernetes cluster. Go to your Polar Deployment project, Polar Deployment, navigate to the Kubernetes Platform Development folder, and run the following command to start a Minikube cluster and deploy the backing services used by Polar Bookshop.
See this code?
Note: if you haven't followed along with the examples implemented in the previous chapters, you can refer to the repository accompanying the book, see this link, and use the projects in Chapter 14/14 begin as a starting point. The command will take a few minutes to complete. When it's finished, you can verify that all the backing services are ready and available with the following command.
See this code?
Let's start by introducing ConfigMaps. Section 14.2.1, Configuring Spring Boot with ConfigMaps. In Chapter 7, we used environment variables to pass hard-coded configuration to containers running in Kubernetes, but they lack maintainability and structure. ConfigMaps let you store configuration data in a structured, maintainable way. They can be version-controlled together with the rest of your Kubernetes deployment manifests and have the same nice properties of a dedicated configuration repository, including data persistence, auditing, and accountability. A config-map is an API object used to store non-confidential data in key-value pairs. Pods can consume config maps as environment variables, command line arguments, or as configuration files in a volume. See this link. You can build a config map starting with a literal key-value pair string with a file, for example .properties or .yml, or even with a binary object. When working with Spring Boot applications, the most straightforward way to build a config map is to start with a property file. Let's look at an example. In the previous chapters, we configured catalog service via environment variables. For better maintainability and structure, let's store some of those values in a config map. Open the catalog service project, catalog service, and create a new configmap.yml file in the Cates folder. We'll use it to apply the following configuration, which will overwrite the default values included in the application.yml file packaged with the application. Configure a custom greeting. Configure the URL for the PostgreSQL data source. Configure the URL for Keycloak.
Listing 14.2, Defining a config map to configure catalog service.
Like the other Kubernetes objects we have worked with so far, manifests for config maps can be applied to a cluster using the Kubernetes CLI. Open a terminal window, navigate to your catalog service project, catalog service, and run the following command.
See this code?
You can verify that the config map has been created correctly with this command.
See this code?
The values stored in a config map can be used to configure containers running in a few different ways. Use a config map as a configuration data source to pass command line arguments to the container. Use a config map as a configuration data source to populate environment variables for the container. Mount a config map as a volume in the container. As you learned in Chapter 4 and practiced since then, Spring Boot supports externalized configuration in many ways, including via command line arguments and environment variables. Passing configuration data as command line arguments or environment variables to containers has its drawbacks, even if it is stored in a config map. For example, whenever you add a property to a config map, you must update the deployment manifest. When a config map is changed, the pod is not informed about it and must be recreated to read the new configuration. Both those issues are solved by mounting config maps as volumes. When a config map is mounted as a volume to a container, it generates two possible outcomes, figure 14.2. If the config map includes an embedded property file, mounting it as a volume results in the property file being created in the mounted path. Spring Boot automatically finds and includes any property files located in a /config folder, either in the same root as the application executable or in a subdirectory, so it's the perfect path for mounting a config map. You can also specify additional locations to search for property files via the spring.config.additional location equals path configuration property. If the config map includes key value pairs, mounting it as a volume results in a config tree being created in the mounted path. For each key value pair, a file is created, named like the key and containing the value. Spring Boot supports reading configuration properties from a config tree. You can specify where the config tree should be loaded from via the spring.config.import equals config tree path property.
Figure 14.2. Config maps mounted as volumes can be consumed by Spring Boot as property files or as config trees.
When configuring Spring Boot applications, the first option is the most convenient, since it uses the same property file format used for the default configuration inside the application. Let's see how we can mount the config map created earlier into the catalog service container. Open the catalog service project, catalog service, and go to the deployment.yml file in the Cates folder. We need to apply 3 changes. Remove the environment variables for the values we declared in the config map. Declare a volume generated from the catalog config map. Specify a volume mount for the catalog service container to load the config map as an application.yml file from /workspace/config. The /workspace folder is created and used by cloud-native build packs to host the application executables, so Spring Boot will automatically look for a /config folder in the same path and load any property files contained within. There's no need to configure additional locations.
Listing 14.3. Mounting a config map as a volume to the application container.
We previously applied the config map to the cluster. Let's do the same for the deployment and service manifests so that we can verify whether catalog service is correctly reading configuration data from the config map. First, we must package the application as a container image and load it into the cluster. Open a terminal window, navigate to the root folder of your catalog service project, catalog service, and run the following commands.
See this code?
Now we're ready to deploy the application in the local cluster by applying the deployment and service manifests.
See this code?
You can verify when catalog service is available and ready to accept requests with this command.
See this code?
Internally, Kubernetes uses the liveness and readiness probes we configured in the previous chapter to infer the application's health. Next, forward traffic from your local machine to the Kubernetes cluster by running the following command.
See this code?
Note: the process started by the kubectl port forward command will keep running until you explicitly stop it with Ctrl+C. Now you can call catalog service from your local machine on port 9001, and the request will be forwarded to the service object inside the Kubernetes cluster. Open a new terminal window and call the root endpoint exposed by the application to verify that the polar.greeting value specified in the config map is used instead of the default one.
See this code?
Try also retrieving the books from the catalog to verify that the PostgreSQL URL specified in the config map is used correctly.
See this code?
When you're done testing the application, stop the port forward process, Ctrl+C, and delete the Kubernetes objects created so far. Open a terminal window, navigate to your catalog service project, catalog service, and run the following command, but keep the cluster running, since we're going to use it again soon.
See this code?
Config maps are convenient for providing configuration data to applications running on Kubernetes. But what if we had to pass sensitive data? In the next section, you'll see how to use secrets in Kubernetes. Section 14.2.2. Storing sensitive information with secrets, or not. The most critical part of configuring applications is managing secret information like passwords, certificates, tokens, and keys. Kubernetes provides a secret object to hold such data and pass it to containers. A secret is an API object used to store and manage sensitive information, such as passwords, OAuth tokens, and SSH keys. Pods can consume secrets as environment variables or configuration files in a volume. See this link. What makes this object secret is the process used to manage it. By themselves, secrets are just like config maps. The only difference is that data in a secret is usually base 64 encoded, a technical choice made to support binary files. Any base 64 encoded object can be decoded in a very straightforward way. It's a common mistake to think that base 64 is a kind of encryption. If you remember only one thing about secrets, make it the following. Secrets are not secret. The configuration we have been using to run Polar Bookshop on a local Kubernetes cluster relies on the same default credentials used in development, so we won't need secrets yet. We'll start using them in the next chapter when deploying applications in production. For now, I want to show you how to create secrets. Then I'll go through some options you have for ensuring that they are adequately protected. One way of creating a secret is using the Kubernetes CLI with an imperative approach. Open a terminal window and generate a test credential secret object for some fictitious test credentials, user password.
See this code?
We can verify that the secret has been created successfully with the following command.
See this code?
We can also retrieve the internal representation of the secret in the familiar YAML format with the following command.
See this code?
Note that I rearranged the preceding YAML to increase its readability and omitted additional fields that are not relevant to our discussion. I want to repeat this. Secrets are not secret. I can decode the value stored in the test credential secret with a simple command.
See this code?
Like config maps, secrets can be passed to a container as environment variables or through a volume mount. In the second case, you can mount them as property files or config trees. For example, the test credential secret would be mounted as a config tree because it's composed of key-value pairs rather than a file. Since secrets are not encrypted, we can't include them in a version control system. It's up to the platform engineers to ensure that secrets are adequately protected. For example, Kubernetes could be configured to store secrets in its internal ET2D storage encrypted. That would help ensure security at rest, but it doesn't solve the problem of managing them in a version control system. Bitnami introduced a project called Sealed Secrets, see this link, aimed at encrypting secrets and putting them under version control. First, you would generate an encrypted sealed secret object, starting from literal values, similar to what we did for the plain secret. Then you would include that in your repository and safely put it under version control. When the sealed secret manifest is applied to a Kubernetes cluster, the sealed secrets controller decrypts its content and generates a standard secret object that can be used within a pod. What if your secrets are stored in a dedicated backend like HashiCorp Vault or Azure Key Vault? In that case, you can use a project like External Secrets. See this link. As you can guess from its name, this project lets you generate a secret from an external source. The external secret object would be safe to store in your repository and put under version control. When the external secret manifest is applied to a Kubernetes cluster, the external secrets controller fetches the value from the configured external source and generates a standard secret object that can be used within a pod. Note: if you're interested in learning more about how to secure Kubernetes secrets, you can check out Chapter 7 of GitOps and Kubernetes by Billy Yuen, Alexander Matyushentsev, Todd Ekenstam, and Jesse Suin, Manning, 2021, and Kubernetes Secrets Management by Alex Soto Bueno and Andrew Block, Manning, 2022. I won't provide more information here, since this is usually a task for the platform team, not developers. When we start using ConfigMaps and secrets, we must decide which policy to use to update configuration data and how to make applications use the new values. That's the topic of the next section. Section 14.2.3. Refreshing configuration at runtime with Spring Cloud Kubernetes. When using an external configuration service, you'll probably want a mechanism to reload the applications when configuration changes. For example, when using Spring Cloud Config, we can implement such a mechanism with Spring Cloud Bus. In Kubernetes, we need a different approach. When you update a config map or a secret, Kubernetes takes care of providing containers with the new versions when they're mounted as volumes. If you use environment variables, they will not be replaced with the new values. That's why we usually prefer the volume solution. The updated config maps or secrets are provided to the pod when they're mounted as volumes, but it's up to the specific application to refresh the configuration. By default, Spring Boot applications read configuration data only at startup time. There are three main options for refreshing configuration when it's provided through config maps and secrets. Rolling restart. Changing a config map or a secret can be followed by a rolling restart of all the pods affected, making the applications reload all the configuration data. With this option, Kubernetes pods would remain immutable. Spring Cloud Kubernetes Configuration Watcher. Spring Cloud Kubernetes provides a Kubernetes controller called Configuration Watcher that monitors config maps and secrets mounted as volumes to Spring Boot applications. Leveraging the Spring Boot actuator/refresh endpoint or Spring Cloud Bus. When any of the config maps or secrets is updated, the Configuration Watcher will trigger a configuration refresh for the affected applications. Spring Cloud Kubernetes Config Server. Spring Cloud Kubernetes provides a configuration server with support for using config maps and secrets as one of the configuration data source options for Spring Cloud Config. You could use such a server to load configuration from both a Git repository and Kubernetes objects, with the possibility of using the same configuration refresh mechanism for both. For Polar Bookshop, we'll use the first option and rely on Customize to trigger a restart of the applications whenever a new change is applied to a config map or a secret. I'll describe that strategy further in the next section of the chapter. Here we'll focus on the features offered by Spring Cloud Kubernetes and its sub-projects. Spring Cloud Kubernetes, see this link, is an exciting project that provides Spring Boot integration with the Kubernetes API. Its original goal was to make it easier to transition from a microservices architecture based on Spring Cloud to Kubernetes. It provides an implementation for standard Spring Cloud interfaces used for service discovery and load balancing to integrate with Kubernetes, and it adds support for loading configuration from config maps and secrets. If you work on a greenfield project, you don't need Spring Cloud Kubernetes. Kubernetes provides service discovery and load balancing natively, as you experienced in Chapter 7. Furthermore, Spring Boot supports configuration via config maps and secrets natively, so there's no need for Spring Cloud Kubernetes, even in this case. When migrating a brownfield project to Kubernetes, and it uses libraries like Spring Cloud Netflix Eureka for service discovery and Spring Cloud Netflix Ribbon or Spring Cloud Load Balancer for load balancing, you might use Spring Cloud Kubernetes for a smoother transition. However, I would recommend refactoring your code to leverage the native service discovery and load balancing features from Kubernetes rather than adding Spring Cloud Kubernetes to your project. The main reason why I recommend not using Spring Cloud Kubernetes in standard applications is that it requires access to the Kubernetes API server to manage pods, services, config maps, and secrets. Besides the security concerns related to granting applications access to the Kubernetes internal objects, it would also couple the applications to Kubernetes unnecessarily and affect the maintainability of the solution. When does it make sense to use Spring Cloud Kubernetes? As one example, Spring Cloud Gateway could be enhanced with Spring Cloud Kubernetes to get more control over service discovery and load balancing, including automatic registration of new routes based on services metadata and the choice of load balancing strategy. In this case, you could rely on the Spring Cloud Kubernetes Discovery Server component, limiting the need for Kubernetes API access to the Discovery Server. Spring Cloud Kubernetes really shines when it comes to implementing Kubernetes controller applications to accomplish administrative tasks within the cluster. For example, you could implement a controller that monitors when config maps or secrets change and then triggers a configuration refresh on the application using them. As a matter of fact, the Spring team used Spring Cloud Kubernetes to build a controller that does precisely that, the Configuration Watcher. Note: Spring Cloud Kubernetes Configuration Watcher is available as a container image on Docker Hub. If you'd like to know more about how it works and how to deploy it, you can refer to the official documentation. See this link. Besides the Configuration Watcher, Spring Cloud Kubernetes provides other convenient off-the-shelf applications for addressing common concerns of distributed systems in Kubernetes. One of them is a configuration server built on top of Spring Cloud Config and extending its functionality to support reading configuration data from ConfigMaps and secrets. It's called Spring Cloud Kubernetes Config Server. You can use this application directly, the container image is published on Docker Hub, and deploy it on Kubernetes following the instructions provided in the official documentation, see this link. As an alternative, you can use its source code on GitHub as a foundation to build your own Kubernetes-aware configuration server. For example, as I explained earlier in this chapter, you might want to protect it via HTTP basic authentication. In that case, you could use your experience working with Spring Cloud Config and build an enhanced version of Config Service for Polar Bookshop on top of Spring Cloud Kubernetes Config Server. In the next section, I will introduce Kustomize for managing deployment configurations in Kubernetes.